Anyway, welcome everybody. Thank you very much for coming. I'm very pleased to announce today's speaker, who's Rasmus Jaksland, who's a PhD student at the Norwegian University of Science and Technology in Trondheim, where he is pursuing a PhD on the project, The Prospects of a Scientific or Naturalistic Metaphysics. Yeah. And he's also a member, an affiliated member of the Geneva Symmetry Group, as you all know, and has done, before he went to Norway, his undergraduate degrees, both a Bachelor in Physics Philosophy at the University of Copenhagen, and then an MA in Philosophy and a Master of Science in Physics, both in Copenhagen, the physics one at the Niels Bohr Institute in Copenhagen. And so we're very, very pleased to have you here, and he will be talking today about entanglement as the world-making relation. Please, Rasmus.
Thank you. All right, so let's get right to it. So this talk, in a nutshell, is based on a recent paper by Michael Esfeld, who wants to argue for the most meager ontological dyad that we can have and still have an ontology that is coherent and adequate. And he argues that this is an ontology that is comprised of matter points that is related and individuated by a distance relation. Okay, so the reason I'm interested in this is because this seems to be problematic from the point of view of non-spatial theories of quantum gravity. So if we suppose that our fundamental theory turns out not to have distance and its fundamental level, then it seems to be a problem of the metaphysical salience of such a theory if the minimal ontology, as Esfeld calls it, is one that has a distance relation. So the solution I want to propose is that we can actually do the same things that we do with distance, or that Esfeld do with distance. We can do them with entanglement instead. So I want to defend that entanglement can replace distance as the world-making relation. All right. So first, I'll give a few comments about this minimalist ontology, then say a few things why distance is a nice relation to build up the world with, and then say something a bit about entanglement before going into the details of defining entanglement and then arguing for some properties of entanglement that will ensure the empirical adequacy of entanglement, or at least that entanglement is as empirically adequate as distance. Finally, there's an obvious problem for this idea that entanglement is a world-making relation, namely that we seem to have extension or distance in our world. And the final part of the talk will therefore concern how to get extension from entanglement. So how to build up extension from this basic world-making relation entanglement. And it will go through some different suggestive arguments at most, I think. There are no conclusive arguments here, but you employing first data CFT correspondence and then the ER equals EPR conjecture due to Maldacena and Susskind, and then finally I'll try to wrap it up. But let's get to the first part. All right, so a primitive ontology, according to Esfeld, is an ontology that is coherent and empirically adequate. And importantly, it's, it seems no controversial things yet, I think. So one of the important things is that it has to be a naturalized metaphysics. So at least this ontology must accord with our best physical theories, or at least a maximal class of consistent physical theories. Okay. And a minimal ontology, a minimalist ontology, is then an ontology that is minimally sufficient to be a primitive ontology. So we should try to see how few elements we have to put into an ontology such that it's still empirically adequate, coherent, and accord for our best physical theories. The promise is not that from this minimalist ontology that we can get all our physical theories. It's just that we can put a dynamics on top of this ontology that then builds our world as it actually appears to us with laws of physics and so on. So it's not that all these dynamics has to be built into this primitive ontology. All we require is that this primitive ontology somehow grounds this dynamics that we then find in all our physical theories of the world. All right. So what Esfeld proposes is an ontology that is defined by these two axioms. So he writes, there are distance relations that individuate simple objects, namely matter points. And then he has an additional axiom, namely the matter points are permanent, with the distances between them changing. So according to Esfeld, this is an ontology that is empirically adequate, coherent, and which, due to its empirical adequacy, actually is in accord with all our best physical theories. Perhaps disregarding quantum gravity, and Esfeld is aware of this himself. So one of the good things Esfeld observes about this minimalist ontology is that it sits well with an empiricist view that the experimental evidence in physics comes down to relative positions of discrete objects and motion. That is, change of relative positions. So this is an ontology where we have distance as a world-making relation, and it accords well with the fact, or the apparent fact, that all our experimental evidence is really just observations of change of distance. So this essentially is the view that I want to object to, or at least offer an alternative account of. But there's some work to be done first. So initially, Esfeld observes that this is an ontology, this distance matter point ontology, is one that endorses a plurality of objects. And he says that's a good thing because we have a plurality of objects. And it's individuated by the distance between an object and then all the other objects. So it's the way we individuate these different objects. Then it's something that can account for the evolution of the configuration or the evolution of the universe. And this is done by token of our world-making relation being quantifiable. So we can change the distances between matter points, and that's what is supposed to build up all the dynamics. And then finally, and this is sort of the good thing about distance relation, and what's the difficult thing about entanglement as a world-making relation, is that the distance relation qualify as providing for extension. And this is just by definition. So the distance relation is subject only to a minimal spatiality or extension constraint. So extension or distance is by definition satisfied this by the distance relation. So this is sort of the empirical adequacy, or the central aspects of this empirical adequacy that Esfeld finds necessary to explain for a minimalist ontology. Okay. Distance is nice because it has a lot of good structuring properties. So it's quantifiable as a non-negative scalar, it satisfies triangle inequalities, it connects, meaning that all matter points are related to all other matter points, it's irreflexive, and it's symmetric. So these are nice properties of the distance relation and the properties that make sure that these empirical adequacy conditions can be satisfied. And these are sort of the ones we'll try to look at in the context of entanglement as well, and see how far we can get with entanglement in getting back some of these elements. All right. So another thing that is, I think, good for Esfeld is that he has Einstein on board. So Einstein says that without an assumption of the mutually independent existence of spatially distant things, physical thought in the sense familiar to us would not be possible. So what Einstein is arguing, at least according to Don Howard, is that the only conceivable objective way to achieve individuation is via separability by distance. So we can't, according to Einstein, have anything else than distance as our world-making relation. Of course, Einstein didn't formulate it in this way, but it's sort of the impression we get from, or it's the impression that Howard conveys of Einstein's views on this. So you can say distance is a likely candidate as the world-making relation. It has nice properties, and it has both Michael Esfeld and Einstein on board. Okay. So what I'll propose is something else, namely that we can replace distance with entanglement. So I have two axioms as well. There are entanglement relations that individuate simple objects, namely matter points. The matter points are permanent, with the entanglement between them changing. And to sort of get this going, we can go through this to-do list. So first we have to demonstrate that we can actually define entanglement independently of distance. And then we have these empirical adequacy conditions that Esfeld proposed. We have to be able to individuate matter points. We have to be able to account for change. And then we have somehow to provide for extension. And the first two we'll try to satisfy by offering some structuring properties of entanglement. And then finally, the extension will more or less be explained away rather than be explained. But we'll get to that in the final section. All right. So first, entanglement. So entanglement can be presented something like this. So we have two people, Alice and Bob, and they just have a particle. It's a spin half particle, so it can be spin up or spin down. They have this particle in a superposition state. Once they measure it, it will be either spin up or spin down. So Alice and Bob does a lot of these independent measurements of their respective particles. But once they meet and discuss the experiments they're carrying out, Alice and Bob finds out that there is a correlation between the measurements they've made. So this correlation is what we describe as entanglement. Apparently the particles that Alice and Bob were measuring were entangled in such a way that we had a statistical correlation between their spins. Okay. So we have this definition of entanglement, or this explication of entanglement, in terms of the statistics as they show up in experiments on these entangled particles. All right. So one worry here is that, at least if we adopt this empiricist view that Esfeld proposed, then the statistics of experimental results seems to presuppose distance insofar as these are measurements made. We think we put it into our spin measuring machine, and the spin measuring machine will have an arm going left or right or up or down, and this change of relative position is then actually the measurement being done. And if this is our definition of entanglement, then this is not an independent definition of entanglement from distance. And therefore, it would be very strange to propose that entanglement then was the world-making relation and distance was derivative thereof. All right. And this seems to accord well with us what Esfeld says about entanglement and mass and charge. So we say they are defined in terms of the effects that they bring about under certain conditions. In other words, by the functional or causal role that they exercise in the evolution of the objects to which they are attributed. So the challenge immediately is to come up with some other way to explicate or define entanglement. And the way to do this is to begin another place. So we begin with a Hilbert space and observe that we can decompose any Hilbert space into two subregions, or into two different Hilbert spaces, such that the direct product of these two Hilbert spaces comprises the full Hilbert space. Now, if we know the state of the system, we can define a reduced density matrix for one of these subsystems characterized by either the Hilbert spaces, so HA or HB, and in this case, we're interested in the density matrix for the Hilbert space HA, and we can define this in this way. This is basically taking the density matrix for the full system and tracing out degrees of freedom that we find in the subsystem B. All right. And out of this, we get this density matrix. The good thing about this density matrix is that we can ask questions about its eigenvalues. And it turns out that we can define entanglement in this way, that subsystem A is entangled with B, where B is the rest of the full system, if the density matrix has more than one non-zero eigenvalue. So if it just has one eigenvalue, and then that eigenvalue will be 1, then the systems are not entangled. But if there are more than one non-zero eigenvalue of the density matrix, then these systems A and B are entangled. So here we have a definition of entanglement in terms of eigenvalues of density matrices that is purely formal and independent of distance. All right, so we got this far. We have a definition now of entanglement independent of distance. Now, the problem is rather immediate. Entanglement, as presented here, is a relationship between a subsystem and the rest of the system. So it's not a relationship between matter points. If we sort of make a subdivision such that one of the subsystems is one matter point and the other subsystem is the rest of the system, then we can have a relationship between a matter point and all the other matter points. But that's sort of how far we can get with entanglement, at least manifestly. But we can do different tricks. Yeah, so first let's observe, let's consider these properties that we had of distance. So at least manifestly, entanglement doesn't satisfy any of these properties.
So I have a quick question.
Yeah.
Why is it that a point in X is not at the zero distance from itself? Is that just a stipulation?
Oh, sorry, it's an artifact of previous formulation. It's a typo. So it is it is irreflexive. So its distance to itself is 0. Yes, good. Sorry. Yes. So that's a typo. Okay. The first step to get some of these to be manifest is to quantify entanglement somehow. And we can quantify entanglement using the von Neumann entropy. So the von Neumann entropy is defined like this, and it's always positive. All right. So now we can say we got something that is quantifiable as a non-negative scalar, but it's still not a relationship between anything else but a subsystem and the rest of the system. In order to get something that is a two-place relationship between matter points, we define the mutual information. So the mutual information we define like this, and since entanglement entropy satisfies subadditivity, we find that the mutual information is always positive. So now we have something that is quantifiable as a non-negative scalar. It's symmetric, as seen here. It's connects, so every matter point is related to every other matter point by mutual information. However, it's not irreflexive and it doesn't satisfy the triangle inequality.
But now I'm still confused because now it looks like the mutual information of a point or an element as of itself or to itself is 0.
No, so it's not satisfied. So
yeah, but if it's 0, then it is satisfied.
Yeah, so it's not. Yeah, so this should have the negation in front of it. Yeah, so it's yeah. So it's so if we just put in A and A, we get A plus A minus A, so we get the entanglement entropy of the object itself, which is only 0 in the special case where this is a product state. And I tried to do different things, see if you can construct something that satisfies all these conditions at the same time. And it seems to be very difficult. So I'll just presume it can't be done. But I don't actually know, and there's not a lot of people very interested in doing this. They're interested in comparing different states in the same Hilbert space, not doing this sort of thing. So if anybody knows how to construct something that satisfies all of these out of entanglement entropy, I would be very interested to hear it. All right. So the point I want to make is just to observe that insofar as we can quantify entanglement with the mutual information, we have something that can encode the evolution of the configuration as changes between the matter points. So it can do all this, they can do the same that distance does. So what is really the difficulty, I think, in terms of empirical adequacy is individuation. So what is it that we want from this individuation of matter points? So I think there are two different senses that we should consider. One is strong individuation. So as I say here, given the state of the universe, the world-making relation determines the matter points that comprise the universe. So if we were just given the state of the universe, we would somehow be able to determine what are the constituents of this universe. This is different from what I call weak individuation. So this is just to say that given the matter points that comprise the universe, the world-making relation ensures that we can distinguish these matter points. This obviously is something much weaker than the strong program. But let's start looking at the strong program. Because I think the strong program or the strong individuation is problematic as viewed from quantum mechanics. So I can't really think of any way to do this without a principle of separability. So I think we could maybe achieve strong individuation doing something like this, that we are given a state, and then we try to make subsystems of this of the full system such that we ensure that the full state of the system remains a product state of the state of these subsystems. So we could sort of go on with this and try to find the maximal division such that the full state remains a product state. And then these subsystems that we end up with would arguably be the matter points in this context. So maybe we could do something like this and get an individuation in the form of strong individuation. The problem is that this method presumes separability. And assuming separability entails that one has to abandon locality due to the violation of Bell's inequalities. So if we assume separability and abandon locality, then we end up with something that has to resemble Bohmian mechanics. So if we want strong individuation, then we have to be Bohmians, basically. And this seems, at least to me, to be a contentious metaphysical claim and not something that is obviously true. So I don't think we should require of a minimalist ontology that it satisfies strong individuation. And this is good news, because, at least for this approach with entanglement, because entanglement, I think, at least proper entanglement has to presume non-separability. So the Bohmian notion of entanglement is defined in terms both of the states, the state and the position, and it seems to encode something different than entanglement as we're used to from from the interpretations of quantum mechanics that has non-separability. All right. So with non-separability, strong individuation is just impossible, I think. But I think this doesn't affect weak individuation at all. So we could think of a way to achieve weak individuation with entanglement. Given the matter points, now we've got n matter points, we can assign an n tuple to each matter point, which states the mutual information between this matter point and all the other matter points. So having such an n tuple, we can say that two matter points are the same if their n tuples are identical. So this gives us a means with which to individuate matter points via entanglement in the form of mutual information. And I think this is precisely the same as what Esfeld requires on distance. So he writes, for the distance relation to individuate the matter points, it has to satisfy the following requirement. If matter point I is not identical with matter point j, then the two sets that list all the distance relations in which these points stand with respect to all other points in a configuration must differ in at least one such relation. So this is exactly the same condition we now have, just with replacing mutual information, or replacing distance with mutual information. So I think in both cases we can achieve weak individuation. But it requires, of course, that we give pre-given matter points. But I'm not sure that, or I have seen no reason why we should expect that distance can do any better without assuming separability and therefore committing to Bohmian mechanics. All right.
Can I just ask a quick question about that?
Sure.
So just go. So Esfeld doesn't say tuple there; he says set.
Yeah, true.
But do you think he means tuple?
Yeah, I think he means tuple.
I mean, of course, that's not true in general, but he does say I mean, or at least the way you've described it is that that's something he's imposed as kind of ruling out a kind of.
Yeah. So at least I think that
symmetry.
I think the idea Esfeld has here is just that we are given a list, and somehow it has to be ordered, right? We need to know which distance is the distance to which matter point. So I suppose we need to have a numbering of the matter points, and then somehow we need to know so we need to know on this list what matter points are what each element of the list is a distance between. So this is just what I think he commits to and all I want to commit to.
Okay, so maybe we'll come back to this later, but then it of course seems like it's the order in the list that's doing the individuating and not the distance or the entanglement.
Yeah, let's get back to that. That's an interesting question. Thank you. Okay, so just extension. How to get extension out of entanglement. So anyone who wants like the account how to get distance out of entanglement may be a bit disappointed, because I'm doing away with distance more than explaining distance. So I want to ask how confident we actually are that what we measure is change of relative distance and not something to do with entanglement. So I think the sort of account I want to offer can be compared to a materialist account of consciousness. In some way, materialists are accounting for consciousness, but somehow they are also explaining consciousness away. So put this in another way, anyone who is of the opinion that there is a special quality to distance, some sort of distance qualia, they will not be persuaded by the account I'm going to offer. One reason I find for not presuming that there's distance qualia is that distance qualia seems to require that we would be able to, for instance, distinguish between the ADS side and the CFT side in a world that realizes the ADS-CFT correspondence. Because we seem to have 4 extended dimensions in one and 3 extended dimensions in the other, and if distance has some special qualia to it, we should probably be able to tell the difference between these two. So this is just a heuristic why we should not initially be too confident that there is something like distance qualia, and why we could probably do with something like a materialistic account of distance, i.e. somehow explaining distance away rather than explaining distance as such. Okay. So first, some remarks about the ADS-CFT correspondence. So this is a relationship between an open and a closed stage theory, and it has the most usual presentation of it is in terms of a relationship between 4-dimensional super Yang-Mills theory and then a 10-dimensional type 2B theory. But the point I want to make here is just that what is proposed here is that we got a quantum state living on the boundary of some space-time. And this quantum state is then conjectured to be dual to a space-time such that this space-time is the full space-time that the quantum state is defined on the boundary of. So this picture is trying to summarize it. The quantum state lives here on the boundary, and then we have the dual space-time with this, which is the whole cylinder. That's the image we want to convey here. Now, what we are going to use this for is that we want to subdivide this boundary that the quantum theory, gauge theory, is defined on into two different regions, and we call them B and B bar. And then we define a surface that is a bulk surface that minimizes the area functional and which has its endpoints on the entangling surface between B and B bar. So B tilde is some bulk surface. And the conjecture is then, and it's been proved to some degree, is that the holds of the so-called Ryu-Takayanagi formula, which resembles the Bekenstein-Hawking formula, which says that the entanglement entropy of this quantum system B is equal to the area of this, or is proportional to the area of this bulk surface. All right. And what is interesting is that there are indications that this relationship, this Ryu-Takayanagi formula, generalizes not beyond string theory, for instance, to loop quantum gravity and allegedly to sort of more general generic group field theories of quantum gravity. So the Ryu-Takayanagi formula seems to relate something that has to do with distance or space to entanglement. And this is manifest if we consider the case where we remove all entanglement between these two regions, B and B bar. If we remove all entanglement between them, then the entanglement entropy goes to 0. And which that means, according to the Ryu-Takayanagi formula, that the area goes to 0. So removing all entanglement, space-time pinches. And what happens is that once we remove all entanglement, it is such that no signal can travel from B and intersect a signal traveling from B bar. So somehow entanglement is related to space-time connectivity. So this is sort of the suggestive picture rising out of this, that we got some relationship between, on the one hand, entanglement, and then a re-representation of this in terms of space-time. Okay. This can be put more concretely if we consider, again, the mutual information. So we have here, again, now this is the cylinder looked at from above. This is, again, the boundary. This in here is the bulk. If we consider 2 points, one in B and one in B bar, then if the entanglement entropy of B between B and B bar goes to 0, then the mutual information between small b and B bar goes to 0 as well. So this is just a property of entanglement entropy. However, what is interesting, and what has been shown by Wolf et al., is that if we can consider a properly regularized bulk distance, and this distance also goes to, or a distance between B and B bar, now in the ADS spacetime in the bulk picture. And if we look at this distance, then this distance goes to 0 when the entanglement or the mutual information between B and B bar goes to 0. So apparently there is, sorry, the distance goes to infinity. I said 0, right? Sorry. The distance goes to infinity when the mutual information goes to 0. So removing entanglement seems to increase the distance between these 2 points. So again, this is just suggestive, but it seems to imply that we can have some sort of translation between distance and entanglement. A similar sort of, we'll skip this one, a similar sort of picture is arising out of Maldacena and Suskind's ER equals EPR conjecture. So they write, we argue that the Einstein-Rosen bridge between 2 black holes is created by EPR-like correlations between the microstates of the 2 black holes. We call this the ER equals EPR relation. In other words, the ER bridge is a special kind of EPR correlation in which the EPR-correlated quantum system have a weakly coupled Einstein gravity description. All right. So the point of the ER equals EPR conjecture is that entanglement and wormholes encode the same sort of information about the relationship between two black holes. And Susskind has done some more recent work on this conjecture and found a relationship between the radial coordinate in black hole solutions and then what he calls quantum complexity that is directly related to entanglement. So what Susskind writes is that we see a precise parallel between the phenomena of falling into a gravitational field and operator growth for a strongly coupled chaotic quantum system. Now again, this is just suggestive evidence. But what we can get from this is that we can perhaps at least conceive of the radial coordinate in the black hole spacetimes in terms of operator, as something that is operator growth and not actually a radial distance at all. So of course, again, this is symmetric relation. We could say the same about operator growth, that we could represent that as some distance instead. But the point is just saying there seems to be an opportunity to translate between distances and quantities related to entanglement. All right. So what I will conjecture is that what is usually described as distance, spacetime, and extension can be encoded in a theory as entanglement structure instead. Again, it's symmetric. So if we think of distance as a world-making relation, the idea is that entanglement is a particular sort of change of relative distance. And in my picture of entanglement as a world-making relation, distance is a particular sort of entanglement structure. This doesn't mean that entanglement is identical to distance. It's not such that we can replace distance with mutual information and then everything works out fine. As we saw, distance and mutual information is very different quantitative properties. In general, this translation will be very, very complicated. The point is just there is some way in which to get a distance relation, or something that looks like a distance relation, out of an entanglement structure, and vice versa. All right. So one worry could be that this entanglement account maybe only applies for radial directions. And I think that's a very genuine worry, and I'm not sure I have anything very good to say about that. So maybe this only holds for radial directions in some holographic setting. But at least according to Susskind, there are indications that the ER equals EPR conjecture holds not only for black holes, but for any entangled systems, even empty space. And similarly, on the Ryu-Takayanagi formula, Van Ramstung, who's done most of this work relating the Ryu-Takayanagi formula to spacetime, argues in some recent lecture notes, we can go further, subdividing the boundary into more regions and removing this entanglement between these. The result is that the spacetime splits up into many small disconnected fragments. By removing all the entanglement, the dual spacetime disappears entirely. So there are reasons to doubt this claim by Van Ramstung, and reasons why the Ryu-Takayanagi formula probably breaks down before we end in this scenario where all of spacetime disappears entirely. But the point is that we can sort of remove spacetime bit by bit by removing more and more entanglement. And at least that's suggestive, I think, of this opportunity to reformulate distances and space in terms of entanglement. All right. So here's some remarks about quantum gravity and our initial worry. So the initial worry was that if distance matter points is the only conceivable minimalist ontology, then this would question the metaphysical salience of any quantum theory of gravity that is non-spatial. So maybe people with that felt strongly about metaphysics would be very worried about this, that such theories are not metaphysically salient and therefore they could not be true. What I propose is that maybe we shouldn't be too sure that distance is the only conceivable world-making relation. I think entanglement does very well as a world-making relation, and the good thing about entanglement is that entanglement is low maintenance. Entanglement only requires quantum degrees of freedom. That's everything. And presumably any quantum theory of gravity will feature quantum degrees of freedom. And if they do, they'll feature entanglement. And therefore, they at least feature entanglement, whereas they don't feature distance. And therefore, this seems entanglement as a world-making relation would make such theories, non-spatial theories of quantum gravity, more metaphysically salient. All right. So, a quick question. Does this resolve the issue of getting space-time out of non-spatial temporal theories of quantum gravity? And the simple answer is no, it doesn't. I'll say a bit more. So, what this does is exactly restoring the metaphysical salience of these theories. It still remains for any particular theory to be shown how space-time actually emerges. My conjecture is simply that there are indications that the entanglement relation can ground the distance relation. And this holds, I think, vice versa. It's symmetric. It's just that we shouldn't be too worried. We shouldn't be metaphysically worried about not having a distance relation at the fundamental level of our quantum theories of gravity. All right. So that, I think, was all I had to say about this. Thank you.
Thank you very much. We should first ask the people in Chicago whether they have any questions.
I do, while the others are thinking up their, finalizing their questions. So, everything you said towards the end then about entanglement grounding a distance relation must be presupposing something like a general relativistic background, right? Because in classical spacetime or Minkowski spacetime, I can take a pair of entangled particles and I can separate them as far as I like, and it has exactly no effect on the entanglement. Is that right? So you are thinking that we are in a context of quantum geometry or quantum gravity, something like that?
Yeah.
Can you say a bit more about exactly what is going in, what is assumed?
So the idea would be that if we have these matter points, then we have some sort of, we could say we have some sort of non-spatial lattice. But of course the problem is to actually get these sort of things working if we only have a non-spatial lattice. So there's work done with random tensor networks that seems to support something like the Ryu-Takayanagi formula, but it's still very, very conjectural. But we certainly need to reconsider completely reconsider the sort of ontology that goes into this. And at least in the usual formulation, for instance, of the Ryu-Takayanagi formula, we need a boundary that is, for instance, Minkowski spacetime. So in that case, nothing we do with entanglement affects this Minkowski background. And so from that perspective, this Minkowski's background is there all the time, and apparently it has nothing to do with entanglement. So I think that worry is certainly genuine, and something that has to be worked out in much more detail than what the state of the project is currently at.
So let me just try again.
Yeah.
I think I see what you're saying. So I just had something really sort of simple in mind. I mean, if you just think about non-relativistic quantum mechanics,
yes,
presumably it would be the same in special relativity. You know, if I just have a pair of, Bell-Bohm spin particles that are in a singlet state, so
yes,
they're entangled in just the sort of simplest way you can kind of imagine. In non-relativistic quantum mechanics and in special relativistic quantum mechanics, you can separate them as far as you like.
Yes.
And the level of the state is completely the quantum state is completely unchanged.
Yes.
And so the level of entanglement between those two is completely unchanged.
Yes.
You know, and that's kind of what's weird about entanglement in
Yes.
that sort
Yes.
of context. So that's obviously not the right so then it just can't be the case, right? So that's just, if that's all the physics that I have, it simply can't be the case that entanglement is going to give me a theory of distance, because the distances simply don't supervene on the entanglement.
Yes. So
I can have whatever distance I like for the same entanglement.
So in that case,
my question is, what's the extra physics that you have to sort of, physical assumptions you have to bring in, or what's the physical framework that you have to bring in which it actually starts to look possible that distance would could supervene on entanglement?
Yes. So we need some notion of holography. I think that's undoubted. So we need to say that the distance you're increasing has nothing to do with the entanglement between these two particles. So this is not the distance that it is encoded in the entanglement. The distance is a proper distance through the wormhole that is connecting these two particles in some holographic scheme. And I saw somewhere somebody saying maybe it's all wormholes within wormholes. So it's very, I know this is very conjectural, but the idea is that the distance relation you're increasing has to do with some other entanglement that is unrelated to the entanglement between these 2 points. So this direction in space is then encoded in the entanglement of something else. So this is what is sort of in the idea that Van Ramstonk offers, that we can remove, if we just continue removing entanglement, then we will see that space-time disappears. In Van Ramstonk's scheme, it's not clear that this relies on the Ryu-Takayanagi formula, and there are reasons, I think, to believe that the Ryu-Takayanagi formula breaks down as we continue to remove entanglement, because the energy keeps increasing. But that's another thing. But the idea is something like that we find more and more entanglement that we then remove. And not that what you're saying would be this idea that we could just replace distance by entanglement, and that's certainly not the case. And I think that's perfectly true. So the distance we're increasing when we're increasing the distance between two bell pairs is not the distance relation that is encoded by their mutual entanglement, at least not directly. So it has to be something more complicated in the entanglement structure that is related to that encodes this particular distance.
Okay. And so, for instance, one might think of, concretely about that holographically. So the distance I'm talking about is distance on the boundary, but the distance that's being recovered is distance in the bulk, something like that? Precisely.
And that then I think is what is the idea behind this wormholes within wormholes picture, that then we start asking questions about this other distance, and then maybe we can make a new construction such that this distance is then arising out of other entanglement. But I know of no actual attempts by physicists to work out how this should be done. And I haven't tried myself. I admit that. But it's precisely the sort of worry I wanted to raise when I said this about radial directions. Perhaps this can only account for radial bulk directions, and then this is not making a very strong case for anything other than radial bulk directions, and not really doing the sort of work I needed to do if this is to defend entanglement as a world-making relation. So I concede to everything you say.
Well, if there's 3 radial dimensions, I guess it's okay. Wouldn't that be okay? We don't care about the others. Maybe that explains why there's 3.
Yeah, that could be. But it's something I have to look more into. Right? It's certainly the most immediate problem for this sort of account, that it relies a lot on holography, and it has these sort of problems.
I just finished watching this TV show Dark, so I'm kind of a little nervous about the Einstein-Rosen bridges at the moment, if you've been watching it.
No, unfortunately not.
Anybody else here? No, over to you guys.
Okay, thank you. Geneva questions? Baptiste?
Okay. Thank you. I really like the theory. But I was trying to think what Esfeld will say, and I guess he will say that what you propose is very different from what he has in mind, right? Because you want to have a very simple ontology, very clear with a few primitive notions that you can understand easily and conceptually. And here I think, I mean, the relation of entanglement is not so easy to grasp, right? So I don't know if it will.
Hey guys, we can't hear anything at all. We didn't hear the question, and if there's an answer going on, we can't hear that.
There's no answer yet.
Oh, okay. But
I'll try to recap the question once it's been asked.
Okay, thank you.
Yeah, so I guess it's more like a point that it's very different from what he has in mind, right? And I'm still struggling to understand what would be a clear notion of entanglement, because later you say that in a way you need entanglement to define distance, and the other way around also. I mean, at some point you say something like entanglement may be understood as a form of relative change of distance.
Oh, so that's Esfeld. That's Esfeld. I certainly agree we could conceive of entanglement in that way, but
if you accept this, then it becomes more like a duality, right?
yeah, certainly. I think it's very very likely a duality. So back to your question. So, but Baptiste is asking, or is worrying that distance is a very simple relation and entanglement is a very elaborate relation, and it doesn't seem very minimalist. Is that so? So my response would be, this is the sort of thing we could think Esfeld would say. So my response would be, this is naturalist misconception. So of course we're evolutionarily better suited to, or more familiar with distances, and it's the sort of way that our brain carves up the world and all these things, but it doesn't mean that there isn't an alternative framework. And I'm not sure, it's just because we are more used to the classical picture doesn't mean that the entanglement relation is in itself more complicated. It's just because we conceive of it in terms of these classical relations, or we conceive of it, for instance, in terms of relations. And if we conceive of it in terms of this distance, if we conceive of it in terms of distance, then of course we need this elaborate account that involves statistics and all this. But we could also just say, this is our primitive relation. And then what would you say if anyone, so you could of course say a bit to people saying, well, what's distance? Or you say it's sort of this, if you think of something here and something here, it's sort of the thing in between. But I could do the same with entanglement. You ask me, what is entanglement? Oh, here's something, it's sort of the thing in between. And then I'm not sure who has the right to, the claim to the simple relation. That would be my response, at least.
Julius?
I actually had a very similar question, so I will just follow up on that.
Yeah.
But still, I'm trying to play out imagine Michael has talked about that. It's kind of hard, but I think Michael would still say, oh, but look, this is a very different situation from his scheme, because here you have the whole package of holography and duality, and so this is very, very rich. It's not a diet, it's a feast.
But to get entanglement out of distance, you need the whole package of quantum mechanics, right? So there's nothing, just offer the different distance relation. Nothing tells you that there will be you can't tell from that what entanglement is and that there will be entanglement. So
You also have, you not only have the quantum mechanics in the package, but you also have holography and duality, which are like additional elements of the package.
Yeah. So the argument is that the getting distance from entanglement is theoretically much more elaborate than getting entanglement from distance. Is that sort of the?
Yeah, I guess.
Yeah. Okay, I think I could grant that, but I'm not. Then we should introduce some sort of status. So what is simplicity in terms of these theoretical construction? I think we need something. We need to know something about the dynamics to know whether entanglement is realized in the world made by distance, and we need to know something about the dynamics in order to know whether the distance is realized in the world of entanglement. Put like this, we need the same thing. It just happens that the getting distance out of entanglement requires a more elaborate machinery. So maybe you could say if we're going for a minimalist ontology, then perhaps this could put some weight in on the side of the distance relation, and then I could say that, oh, but it can't account for these non-spatial theories of quantum gravity. So maybe the entanglement relation has more explanatory power. Maybe that would sort of pull in the other direction.
And then, if I got it right, and it's more like a clarification question. Yeah. Under your conjecture, you would say that it's actually equally difficult or equally easy in both cases because the grounding here will be symmetric.
Yeah, that would be that is my intuition. I think I wrote in the abstract that entanglement and distance is metaphysically interchangeable, and so the idea would be that they make the same worlds. I'm not sure that's true, because I think perhaps distance could make, so completely classical worlds apparently doesn't feature entanglement. So you could, so those are worlds that don't have a distance relation, but maybe we could say the same for entanglement. So at least in some cases, they are metaphysically interchangeable. Not meaning that we could just put mutual information instead of distance, but we have to do a very elaborate translation in order to go from one to the other.
I mean, at least for the Lorentzian distance, because the distance that we have in the conjecture is not Michael's distance, right? This is the Lorentzian distance in the ABS 5 times S4 or whatever.
Yeah, so
this in particular does not satisfy triangular homology because it's Lorentzian.
Yes. So I think that comes back to the next question. It relies a lot on elaborating these arguments for the relationships between distance and entanglement in these holographic schemes, in particular to do with these radial directions in holographic settings.
It's also striking that you assume only matter points in a very Esfeldian fashion. So my question was, in the physics you cited, are there really only matter points?
No, so this physics I cite is completely oblivious to this discussion. So they are, for the most part, this is defined on four-dimensional Minkowski spacetime. So this where most of the work on the Ryu-Takayanagi formula has been worked out there, then having a duality to an ADS spacetime, and then, for instance, showing that there is a relationship between constraints on entanglement and the Einstein field equations. And it's another striking feature, but all of this is not done on sort of distinct matter points.
Yeah. Are there many more things than just matter points?
Many more things.
At least in the dual theory, what is related by distance are manifold points, not matter points. And in general, there seems to be, I suspect, you can tell me that.
Yeah, so I think at least if I'm to follow the intuition behind the minimalist ontology, all of this is change of the world-making relation. So in one case, it's change of this basic distance relation, and this is all that the experiment actually comes down to. So these are just ways to make sense of what we actually find in experiments. And I think I could say the same about entanglement. This is just change. This just comes down to changes in entanglement relation between these matter points. And then the rest is just some elaborate structure that we build up in order to have a good way to encode these changes.
Means of representation.
Yeah.
Thank you.
Yeah.
So, by the way, I think in Esfeld's picture, that's a form of relationalism. These are matter points, not manifold points.
Yeah, but what was striking was that he was following Esfeld
Right.
in
No,
his
no,
brief.
I see
Right,
that.
that was
But I think you said manifold.
No, I thought that in the example he was citing because they were discussing the fact that the relation was Lorentzian.
Yes.
In
Yes,
this case,
so
they were
that's
also
in
between.
that case.
And
Okay,
you're
I
right
see.
in the holographic scheme as it's usually discussed. It's spatial regions and entanglement between spatial regions in the conformal field theories that we are exploring.
So I have a question which is maybe a little bit connected to some of the things that Julius mentioned. In Esfeld's view,
Maybe you should move closer to the computer.
in Esfeld's view, you have the matter points and the spatial distances and the dynamics then.
Yeah.
And the way that time comes into that picture is in that it supervenes on the dynamics somehow. It's the dynamics are metaphysically prior and time metaphysically secondary on that.
Yeah.
Now, I'm asking myself what's going on here in that respect. I mean, how do you, it's not just that we need space to get out of this. We need to get time somehow as well. So is it along the ways that you think what you get out here, what you ground is not just a spatial distance relation, but the space-time interval relation or something? In that sense, you would take care of that problem?
Yeah.
Or is it really just spatial, in which case you'll have to tell me something about dynamics or something else that you would get that as well?
Yeah. So on purpose, I tried to make the precisely the same axioms or endorse the same axioms as Esfeld, except replacing distance by entanglement. So my argument would be if Esfeld can get dynamics out of this basic distance relation, then I can get it out of this basic entanglement relation. Because so the idea would be if we just think of Esfeld's picture as comprising of a lot of matter points and then lists that say how they are distanced from each other, we could do precisely the same with mutual information. And then we know about the mutual information between all the matter points, and then we can begin constructing dynamics by allowing change of mutual information.
Okay.
And that would of course require change of the entanglement relations between these, or the entanglement structure of the system.
Okay. But then it might be important that you do get actually exactly the same list of properties that Esfeld gets. If you want to just, take
I'm
out
really
the distance relation, plug in the entanglement relation, and hope to get the same work done, then there's a worry that if you don't have the same list of properties satisfied of that relation, that you won't be able to do it.
Yeah. That's right. So I have to rely on this. The configuration would have to be very different. It's not just that wherever there is a distance, I put in mutual information and then it should work out. I have to say, so these are this distant from each other. I think as Nick pointed out, the mutual information that encodes their distance is not even is probably not even the mutual information that encodes this distance may not have anything to do with these two matter points, at least not individually, but may have to do with some very non-local, a very non-local property of the whole entanglement structure. So in that way, I think you're right. I can't just guinea pig on his. Nick has a follow-up, I think.
Okay.
I think. So it was a concern. Yeah, it was a question I had, but I think it's actually pressing Chris's point a bit here. Yeah, right. So I think we're talking about the part of the slide where you said mutual information quantifies the relation between matter points and entanglement can encode the evolution of a configuration.
Yes.
And the thought I had there, it's not clear to me that, are you saying that the dynamics that we'd like to get out in this situation, and I'm thinking, again, starting from some very simple case where I'm just imagining sort of non-relativistic quantum mechanics.
Yes.
Are you claiming that the quantum state, like the wave function state, supervenes on the sort of entanglement relations between the objects? Because that doesn't seem like it can be true, since they all come out of tracing out.
Yeah.
To find the state of any one, you have to trace out the others. I mean, you're kind of losing information in doing that. So then it doesn't seem to me that you can get it. The dynamics I'd like to be having is the quantum dynamics, and I won't be able to sort of tell just by looking at the entanglement sort of history what the underlying quantum dynamics is.
So I think I have two things to say to that. I think, couldn't the same objection be presented to Esfeld?
I hope
so. If you just were given the history of relations or of distances between matter points, I think we get the same. I think it relates to this issue of that we have to somehow regard all the physics that we usually, all the theories that we're usually working with as some sort of representational device to say something about these relative changes of relation between matter points. Concerning the point particularly, I think you're right. I can't say that we should be realist with respect to the mutual information. We have to be realist maybe with respect to the density matrix of the full system. And of course, that raises the question whether I'm allowing myself much more structure than Esfeld is. And I think that's a genuine point, and one thing I discussed with Augustin yesterday, and that the question is whether the full density matrix of the whole system is not more sort of ontologically involved than just having this list of distances and its changes, and the history of these changes. So I don't know if that addresses some of the concerns.
But I suppose you're right. I mean, Esfeld I guess I should know, but what does Esfeld say about, I mean, if he's thinking Bohmian mechanics in this kind of picture, you need to have the wave function as well, right?
Yeah. So I suppose you have to go, so as Joshua proposes, we have to regard it as some sort of representational device. What is real is actually just these matter points and the change of their relative position. All the other is ways to encode this the actual relative change.
Yeah, it's in the nomological part of the structure.
Yeah. Okay.
And I think I can sort of go the same way here, saying it's just I just have related I just have quantum points, if you want to say that, related by entanglement, and then sort of do the same thing, not saying a lot more about it. But in the paper, there's not a lot of details, and unfortunately, I haven't had the opportunity to read the book yet. But maybe there are more details in the book than in the paper.
I think there are,
Just because the book is not.
That's helpful. I see how you're thinking.
Yeah.
Okay.
Right.
Thank you.
Thank you.
So I have another worry that if this is supposed to be a project in naturalistic metaphysics, why insist at the beginning that entanglement relation is the one thing, regardless of what future physics will tell me then, this is the one which I grab and run with it and try to build up my primitive ontology and everything else on that. Shouldn't we much rather just say, okay, let's first, elaborate on the physical theories, and then let's see which quantum theory of gravity will win out, and then let's study that theory and let's interpret it, and maybe if it's causal set theory, it will be something different from distance as I mean, this may be unlikely, but it's that sort of in that spirit that we don't bother doing too much of that work just yet, because it looks like quantum gravity is not yet really mature enough to be able to do that kind of work.
Yeah, I think that I have two responses. One is a bit foolish, and the other is a genuine one. The problem with that would be that Baptiste and I would be out of work. So if we couldn't do the philosophy of the current state of physics, or the metaphysics of the current state of physics, and we had to wait until physics was finished, then
No, that's not what I'm saying. Not every philosophical work has to wait until quantum gravity is finished.
No.
But maybe that very ambitious world-building sort of work, that may have to work until we know more.
Yes. So one response I can think of is that if we consider this choice between separability and locality, I think we may be able to consider the distance matter points ontology as choosing separability over locality, and then this picture as choosing locality over separability. So at least that suggests to us, very conjecturally, that we have a choice between two different ontologies. I'm not saying that we couldn't maybe build the same out of some other quantum relation, but entanglement offers itself as the most obvious quantum relation in this regard. Once we say we want locality and therefore we can't get separability, okay, then we go with entanglement. So that would be my reason to suspect that we might have sort of offered the two approaches that is actually available. Though it's not clear that the distance matter points has to adopt non-locality. They could do a lot of the same work as I've done here, and therefore it's not clear that there's such a choice.
Okay. Are there more questions in Chicago?
Going once? No, I think that we're good here. Thank you.
Thank you.
Geneva? Well, in that case, please join me in thanking Rasmus again. Excellent. Great. Thank you very much. Bye, Chicago.
Bye.
I'll see you on Saturday, Nick.
Chris.
Yep. Okay. Have a good flight.
Yeah, you too.
Thank
we have
you.
thunderstorms coming here, so.
Oh no. Leave before they come.